Hey folks, today's topic's simple harmonic motion. So basically with simple harmonic motion, we've got motion that's going to be repeating itself after a set period of time. My definition, I started writing it and it got away from being simple. So basically what I would say is simple harmonic motion is any motion where the object has been displaced from its equilibrium position and has a restoring force that acts to return it to its equilibrium position. Basically, a restoring force is any force that points in the opposite direction of the object's displacement. So if we think about things that point in the opposite direction of their displacement, springs come to mind right off the top of the bat. And then the equilibrium position is going to be the rest position, where that restoring force is going to be equal to 0 newtons. So it's not necessarily where it starts, but it is where that restoring force is going to be 0 newtons. Now, simple harmonic oscillators come up a lot in physics, basically because they can model more interesting systems than what we're about to talk about. So we can talk about electronics, quantum mechanical systems, molecular structures, things like that. But we're going to talk about a mass attached to a spring, and a simple pendulum. So, having said that, let's go ahead and talk about a block attached to a horizontal spring on a frictionless surface. Now, we'll start with a horizontal spring, but we will want to talk about a vertical spring later, even though it's a little bit more tricky. So, there we go. That's my block at the equilibrium position. Now, imagine what would happen if I stretch it back. So if I stretch it back, I'm going to get a restoring force back towards this direction due to Hooke's law. So Hooke's law describes the force acting on a spring, and it's negative k, spring constant k, delta x, how far we've displaced it. So the further back I pull, the stronger that force is. And that force is going to diminish to 0 as the block moves this way. Now, as the block's moving this way, it's accelerating, right? So when it reaches that equilibrium position again, so here we are back at the same position, now we've got a velocity that's going in the negative direction. So we've got a non-zero velocity, we're back to 0, we've got no force, inertia is going to keep that moving in the same direction. So now it moves until it stops. Now this shouldn't be too surprising, but it moves the exact same distance as we pulled it back because this is a frictionless surface. If we did have friction, we would expect it to stop before then. And this is also with an ideal spring. Obviously, some springs can't compress as far as you can stretch them. So now we've got our restoring force pointing in the positive direction. So now we're going to be accelerating in the positive direction. When we accelerate in the positive direction, when we get back to our rest position, now we've got a positive velocity. Do we see where this is going? Well, just like Maxine Nightingale, we're right back to where we started from. And then this is going to repeat back and forth, over and over again. So, when we take a look at this, you know what? Let's pull back here and consider some motion graphs. Sorry, the baby's babying. So, when we start out, we've got a positive displacement, right? Then we've got 0 velocity, and we've got an acceleration. So force and acceleration are always in the same direction. It's just the magnitudes changed, right? So this is a force pointing in the negative direction, so we would have a negative acceleration. I'm not really worried about the amplitudes, I just want to show you the shape of this graph. At our next point in time, So I'll move over a block. At our next point in time, well, now our x position is 0, but our velocity is very negative. And our acceleration has gone to 0. Interesting. Now we've got a very negative, very negative here. Our velocity has stopped again, and our acceleration is pointing back in the positive direction. Here we're back at equilibrium, so we're back to 0, but our velocity is now pointing in the positive direction, and our acceleration is back to 0. Then we repeat. So we're going to repeat the same thing, and I'm only going to repeat it twice. So we repeat what we had before all over again. Boop, 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 boop. Oh, hey. Now, if we just connect the dots, we would get like a sawtooth graph, but we should know better than that. Really in between, so as this is accelerating, right? So this should be, it's a negative acceleration, so we get a frowny face curve. And then, we end up with something that looks like a cosine. Now, if I'm a calculus person, and I know that the derivative of my displacement equals my velocity, well, if I have a derivative of a cosine graph, I get negative sine. Okay. My wife just walked past the baby and upset the baby because she did not pay the baby enough heed. So, and then same thing happens for the acceleration. So the acceleration graph, if I take the derivative of a negative sine graph, I get a negative cosine graph. So that's weird. I get sines and cosines. So when we take a look at the period here, we're going to get a period that's 2 pi, and then it's going to depend on two things, right? It depends on how much mass this block has. The more mass it has, the slower the period would be. And then the k constant here, because that determines the force, the more the k is, the smaller it'll be. So it's going to be 2 pi and then mass over our k spring constant value. So that's the period for any mass and spring system. We can also talk about a pendulum. So a pendulum is going to work much the same way. So for our pendulum system, we've got our rest position where we're just hanging down, and this is the video that I did outside. So just trying to draw it out for clarity. So at the rest position, tension's pointing up, weight's pointing down, and there is no net force. Here though, we've got a tension off to the side, our weight's going down, that leaves us with a net force going this way. Then we return to our equilibrium position, and then on the other side, we would get our net force going back the other way. So, just like before, we're going to get the same sort of graph. So if I displace it in the positive direction, I have 0 velocity, and I've got a negative acceleration. Then when I get back to equilibrium, good, now the dog's barking. Then here, I've gone backwards, but I've stopped, my acceleration's in the positive direction. Then we swing back to equilibrium, but now at the equilibrium position we would have a positive velocity and a 0 acceleration. And then we would repeat that pattern all over again. Now, once again, we're going to get a sinusoidal pattern. So it's going to look like that. And we can basically say the exact same thing that we already said. It's going to be, we're looking at the first and second derivative of, we're looking at the first and second derivative of a cosine graph. Now, once again, not surprisingly, that's going to leave us with a 2 pi in our period. Now, the only thing that's going to affect the period of a pendulum is actually the length of the pendulum itself. So that's why pendula were used to construct clocks way back in the day before we had methods that were easier, right? You can't really have a pendulum hanging off your wrist. But in a grandfather clock, you have a pendulum that's adjustable so that you can make sure that you get the period to be exactly 1 second every time it swings back and forth. Now, yesterday, we were measuring a period of about 4.8 seconds for the time it took to swing back and forth. So we can estimate the length then of the swing in my front yard. So if we know t is equal to 2 pi square root of L over G, then t over 2 pi is square root of L over G. I can square both sides. So t squared over 4 pi squared is equal to L over G. And then I've got t squared 4 pi squared multiplied by G is equal to L. So from there, I can calculate how long the pendulum in my front, swing in my front yard is. So 4.8 times 4.8 times 9.8 divided by 4 pi squared is about 39.4, and I get a length of about 5.73 meters. So that would be about 18.6 feet, which makes sense to me. Okay. Enjoy simple harmonic motion.